Good morning, everyone. So, today we'll look at the solution from INMO 21. Okay, so as usual, there are 6 problems and 4 hours to solve it. Okay, so the exam was held, I think, in March first week. So, let's start. So, this is problem 1, and it's actually the easiest problem of the paper. So, basically, you are given a set of uh, set of integers mi and I, such that if you take any two pairs, it will satisfy this relation. Okay, and then it says that find the maximum possible value of r. So this problem is actually the easiest problem of the paper, and I could solve it, maybe in less than a minute. Just by looking at it, I know what to do. So first of all, what does this expression reminds you of? Okay, so does it reminds you of anything? So to me, it reminds the area of a triangle. Okay, so I'll just explain. So if you take O as origin and take the other coordinates mk and k as ak, then the area of triangle OAIAJ is actually given by this expression. Okay, so that's what, if you know this or if you can recall this, then it's actually very easy to solve. Okay, so you can also represent it in terms of vectors. I just mentioned it here in case you want to have a look how the area is related by the vectors. So the area of this triangle, of whose one vertex is at origin, second vertex is mi and I, third vertex is mj and j. The area is this. Okay, so it's half of this, and this is given as 1. So area of this triangle is half. So basically what we are looking at is a lot of triangles which have same area. Okay, so now let's see what to do. So this is given. So I fix first vertex as a1, and the second one I just vary a2, a3, a4, and so on. So area of all of these is half. Okay, so what does it mean geometrically? So these are all triangles which have a common side OA1, and all of them have same area. So where can these other vertices, a3, a4, a5, and so on, where can they lie? So let's just draw figure. So first triangle is this OA1, A2, and now we have OA1, A3, and OA1, A4, and so on, which all have same area as this. It has same side OA1. So where can they lie? So since there is a common base, so they all have to lie on the same height as A2. Okay, so it can lie on basically on this line. Can it lie somewhere else? So it can also lie on the other side at the same height. So if A3 lies on this line, then the area will be the same. Okay. Similarly for A4, A5. So all the points basically have to lie on this or this. So this is the relation you get. And now you fix A2 and vary again. Fix A2, vary A3, A4, the third one. So all this area is half. Area of O, A2, A1 is also half. So all these triangles, they have same area half. So all these triangles have side OA2 common. Okay. So where can the vertices, all these three lie? So it lies on OA2 is this base which is common. So it has to lie on the same distance as A1. So it basically has to lie on this line or at this line which is at the other side. Okay, at the same distance. So A3, A4, A5, they all should also lie on L3 union of these two. Right? So where can they lie? So they can only lie on these 4 points, the intersection of these two lines and these two lines. Okay, so since the point has to lie on this or this and this or this, so you take an intersection of these two. So there are only 4 possible points where all these other vertices can lie. So you can put A3, A4, A5, A6, but is that the answer? Is r equal to 6? No, because if you put A3 here, you cannot put A4 here, because the area of OA3, A4 is going to be 0. Okay, they're all in the same line. And if you put A3 and A4 adjacent to each other, if you put it here and here or here and here, and then in this case the area of any of these sectors is actually double of that. You can see that. Okay, so actually there is no place for A4. Once you fix A3, you cannot put A4 anywhere. Okay, that's the idea, and that means R can only be 3. Okay, so that's this problem. It's a very simple problem, and if you can just converge geometry, it's actually very simple. And that's it. There is a IMO problem from I think 95. I made a video on it. It's problem 3, which is based on the same idea as this, but of course it's much harder. And if you want, you can just go and have a look. So, all right, let's move to the next one. So this is, again, it's not so difficult. It's actually, so there are two cubic polynomials. Okay, the x squared term is basically 0, and the coefficients are a, b here, and it's reversed on this one. So it says find all the integers a, b, so that all the roots are also integers. So for you used all the relation of the roots, the Vieta relations, so the sum of roots is going to be 0 on this and 0 on this, because the x square factor is 0. So you take the roots of this as alpha, beta, and minus of alpha, beta. For this, you take gamma, delta, and minus gamma plus delta. Just trying to reduce the number of variables. So after this, you write the other two relations. So A, you can write the sum of, you take the product, pairwise product, and the sum of that. So it's alpha into this plus beta into this plus alpha beta. It will turn out to be this. And A, you can also write from here. It's actually the product of these three roots with a minus sign. So it's gamma delta into gamma plus delta. Same for B you can write. And what you can notice is that these two expressions, they're always even. Okay, because if one of them is even, of course it's even. If both are odd, then the sum is even. So this one is always even. That means this is also even. Okay, and when can this be even? Only if the difference is even. And when is the difference even? If that is when both are odd or both are even. Okay, so if both are odd, then of course this sum alpha plus beta is even, so the difference is basically it's odd. And if both are odd, then if both are odd, then this is odd, this is even. So the difference is odd. And if both alpha beta are even, then this is even, this is even, so the difference is also even. So all this alpha beta gamma delta, they are all even. So now you can write or alpha, you can write 2 of alpha 1 and so on. So all this factor of 2 will be there. And now you just plug it back in. So this you can now write as 4 times of a1, where a1 is now in terms of alpha 1 and beta 1. So you have just pulled out a factor of 4 here. And this is what you get. So this is basically, now you get the very same expression and use the same logic that these two are even. So that means alpha 1, beta 1, gamma 1, delta 1, they are also even. And then a1, you can write it as 4 times of a2 and so on. So this series you can continue. So and this is like infinite descent. So if it's anything anything finite, so then this series will diverge to infinity. So the only possibility is that all these terms are 0. So AB must be 0. Okay, so that's the only solution. And this problem is also done. So let's go to the next one. So this is they have mentioned Vikram Betal. So the Betal marks 2021 points on a plane. No 3 are collinear, and after that he chooses, and he draws possible line segments for all of those, and then he chooses around 1011. So if you double it, it will be 2022, one more than that. Okay, so of these line segments, and it marks their midpoints. Okay, finally he chooses line segment whose midpoint is not marked and challenges Vikram to construct a midpoint only using a straight edge. Okay, so Yeah, so this is so this problem is yeah, I liked it. You need to do a little bit of research in order to solve it. It's not immediately obvious what the solution is. But of course, what I realize is that there are actually many solutions, and even if you think think in many directions, it's possible that you'll find a construction. So I will just show you one construction which I thought is the simplest. I found three, four constructions, and out of that, this one was the simplest one. So I'll just show you that. So key observation is this. So he has chosen 1011 line segments. So there are 2022 endpoints, but there are only 2021 points in the plane. So that means there are two line segments which have a common endpoint. So this arrangement exists. Okay, and he has marked the midpoint of this. And what so basically you have to choose this, and from this you have to start your construction. So first thing you can do is you join this, and the thing is, can you find the midpoint of this one? So this is, of course, it's possible, because if you join these two, then this is the centroid, and if you join the centroid and one vertex, it will go through the midpoint of this. So this so there, with this method you can construct the midpoint of the third segment, and basically now you have a triangle with the midpoints of all the three sides. Okay, so and after that, now it's given any line, any other line. Can you find its midpoint? So the answer is that with this, just with this, you can find the midpoint of any other line segment. Okay, it's possible. So I'll just show you. I'll just show you one construction. So let's start. So this is what we have found, and there is this line segment and we want to find the midpoint of this. Okay, so how do we do this? So first thing I do is, so first thing you notice that this side, this segment, it cannot be parallel to all three of them. Okay, so there are two sides. If you just extend it and you extend this segment, they will intersect somewhere. Okay, so you do that, you extend this, they intersect, and after that what you do is you join two opposite segments here. Okay, and now what you can do is you can join the midpoint of this and midpoint of this and extend it. So in this triangle, this is the midpoint, so this line is parallel. Okay, and if the parallel line is extending here, this parallel to this, it will meet this third line which comes from the same vertex, so it will hit it at the center. Okay, so this result, I'm sure you know it. So by extending this, I can construct the midpoint of this, and since in this triangle now I know the midpoint of two sides, I can also construct the midpoint of the third side. So that's by using this centroid method. Okay, so I join this, join that, and then I find the centroid, and I join this, and I find the midpoint of this segment. So midpoint of this segment is also found, and after that, what we do is I remove this. What I need to do is I join this. First time we joined this, now I also join this one, and again the same thing. I join these two lines, move it forward. It will be parallel to this, and it will hit it at the midpoint of this. So I also found the midpoint of this one. Okay, so that's what. And after that, what I do is I just join the endpoint of these two segments to this vertex. And now if I join this, so this is like, a lot of rays are coming out of this point, and this is the midpoint, so this segment is going to be parallel to this, so it will hit it at the midpoint of these two segments also. So this line will hit it at the midpoint of these two segments. So we found the midpoint of this, we found the midpoint of this. So, and now I again use the centroid trick in this triangle, and I find the midpoint of the segment that I need. Okay, so this was. I hope you found it simple. So basically, when I constructed it, I actually joined this two of these to one of the sides, and then I tried out a few things, and then I saw that this works. So. Okay, so was problem three. The problem was simple, but it will take some time to find it out. This is like a research type problem. Okay, sorry. Yeah, so this is problem four. This is also simple. So there's a magician and detective are playing a game. It lays down. The magician lays down cards number 1 to 52 face down on a table, and on each move, the detective can point to two cards and inquire if the numbers on them are consecutive. Okay, the magician replies truthfully. Okay. After a finite number of moves, the detective points to two cards. She wins if the numbers on these two cards are consecutive and loses otherwise. Then it says prove that the detective can guarantee a win if and only if she's allowed to ask at least 50 questions. Okay, so the best way to deal with such problems is to convert it in a graph. Okay, so the 52 cards can be represented as the edges and the as the vertices, and the edges will represent the answer. Okay, so and I've marked some as blue, some as black. So the black means the answer will be a no if you inquire between two cards. If the answer is no, it's a black line. If the answer is yes, then it's a blue line. Okay, so here what you have to there's a small care that you have to take is that these numbers, these 1 to 52, they do not represent the position of the card. They actually represent the numbers. Okay, that's important because this is an important thing here, because if they represent the position, then you are not sure where these blue lines are actually. Okay, and these blue lines are the ones that you are interested in finding. Okay, so if these are vertices, then the problem becomes it's more difficult to solve. So, but if the vertices represent the numbers that are on the cards, then you know that you are actually interested in actually the finding out where the outer shell is. Okay, so now this problem is quite simple. So the black line represents the answer is no, and the blue line represents the answer is yes. And every time you ask a question, you are basically detecting one of those lines. And the thing is, how many minimum questions that you need to ask in order to guarantee that you have detected a blue line. So there are 50 lines that you need to detect in order to guarantee the detection of a blue line. So because there are 51 lines from every node, so if the 50 lines are black, turn out to be black, then you know that the 51st line is actually a blue one. Okay, so obviously you have to detect 50 lines. And what is the strategy? The strategy is that you stick to a node, and then you keep asking questions about it with respect to the other nodes. Okay, so you fix one card. Let's say first card. Okay, first here means position, not the number. You do not know where the number one is. You just fix the first position. Maybe it's anything. Maybe it's number 3. Maybe it's number 51. Anywhere, and then you ask between the pairs first and second, first and third, first and 51. So if all of them are no, then the first and 52nd card are the consecutive ones. Okay, so that's a simple problem, but you should know that how to make the graph. You can make it with respect to the position, and also with respect to the numbers that are actually on the card. Okay, so in one, if you do one, the problem is very difficult to solve. If you do the second one, then the problem is actually quite easy. Okay, so yeah, so if the answers to all of them are no, then of course you know that first and the last card are consecutive. So that's the thing. This is problem 5. This also I really liked it. So it says there is a quadrilateral ABCD, and you are given the angles ABD is 30, BCA is 75, this BCA is 75, ACD is 25, so ACD, this one is 25, and CD equals CB, so these two edges, they are equal, and then it says extend CB to meet the circumcircle of triangle DAC at E. So you draw the circumcircle of DAC. You draw it and extend CB to meet it at E. So you extend it to E. And then it says prove that CE equals BD. So this line CE is equal to CE equal to BD. So since I've drawn a red over the blue, this has become violet. So anyways, so this line CE is equal to BD. This one. That's what you got to prove. So this problem, you have to make a few observations here. I mean, the first thing is that this is isosceles. So that means, and this angle is 100. So these two other angles are 40, 40. Okay, that you can detect easily. And this is 70, this is 75. Now you also know what is this angle here. So this is 35. Okay. And you're not immediately sure about the angles, these two angles here. So the solution of this problem requires in a very clever construction that you need to do somewhere. And how you detect, or how you can think about that construction is that you have to have a hunch that the center of this circle, it probably lies on this side AB. So of course, since this angles are strange, you cannot just draw it with a compass. I mean, I don't know if they allow protractors at the hall. I think not, but you can only approximately construct it in the exam hall. So you'll see that maybe the center, when you draw it, you'll probably see the answer. The center probably lies very close to this, and from there you kind of have to make a guess that the center of this arrangement of this circle, it lies on this line AB. Okay, and if the center lies on this, and if you can detect it, you can draw a lot of radius, and they're all like equal sides, so you have a lot of isosceles triangles and all that, and that should simplify things. So that's that's like you have to start it with a guess. And you can also have a look at if these angles, do these numbers actually make sense. So this is 70, this is 35, so this is half of that. Okay, so this observation, if you make, then also it can maybe help. So if the center lies on this, and since this is the largest one, I decided to make it from this. So I want to cut off a segment which is equal to this, which is this segment here equal to a segment here. I want to cut off that. So the way to do it is, of course, you make construction, either make a perpendicular bisector, or you just cut off 35 from this. So this construction you make, and so that this side is equal to this side. So you make this construction. So you find this point here so that this equals this, either by cutting off the same angle as this, or through any other means. You just draw a perpendicular bisector, and such. So whatever means you draw this equals to this, and now this becomes 35, this becomes 40, and what you notice is that this also becomes 70, this becomes 35, 35, 70. So this triangle is now isosceles because this is 70, this is also 70. Okay, so this was blue, this is now blue, this is blue, this is blue. So all these sides, they are all equal now. And now you look at this triangle, CDCO. Remove this one, join this. So this is an isosceles triangle, and the apex angle is 60. So that means other two angles are also 60. That means this is actually an equilateral triangle. Okay, so this is isosceles. That means this is equilateral. That means This segment also has same length as the other two. So that means all these blue lines, they're all equal everywhere. So this also means that this O is actually the center of this circle because it's at the same distance from all these 3 points. So what you have shown is that O is the center and the center lies on this. So you have seen this, and after that it's actually, yeah, it's actually quite easy. You join OE, just remove, so yeah, so these two sides are equal. This angle is 40, so this is also 40, and now you just remove this and you look at this triangle BDC and COE. So they have two sides common, I mean two sides of same length and two angles same, so they are basically congruent. So if they are congruent, the corresponding side DE, DB and CE, they are equal. So these two red lines, they are equal. Okay, so yeah, so the trick is to find that construction, and once you can do that, then it's actually straightforward. So this is the last one. It's a problem on functional equations. So usually students find this kind of problem, it's difficult to do. Yeah, they don't know where to read it. There are not too many books, and so the way to do it is, of course, there are few things that when you deal with functional equations, there are few things that you can read as theory, and there are some things which theory cannot explain. You have to keep on playing with the relations that's given, and you keep on keep on moving further till you exhaust all possibilities, and then whatever remains that's has to be your answer. So basically, yeah, so let's have a look at these this one. So it says Rx is a set of polynomials with real coefficients. So find all functions f from Rx to Rx satisfying the following condition. The f maps 0 polynomial to itself, so it maps the 0 polynomial 0 to 0. Okay, for any non-zero polynomial p, degree of f of p is less than equal to degree of p plus 1. Okay, so if p has degree n, then f of p has degree n plus 1 or less. Okay, and for any polynomials pq, p minus fq and q minus fp have same set of real roots. Okay, so what you do is you start off with basically some small things. So of course it's given f of 0 is 0. So f of 0 is 0. Here you put, and then you start playing with this relation here. Here you put, let's say q equal to 0. Then what do you get? This is 0, this is 0. And then what it means that p and minus fp have same roots, which basically means p and f of p have same roots. So this is already a new insight that you have found about this function, that this function, it maps, when it maps the polynomials, it maps them in such a way that they have same roots. Okay, and then you do something else. You put q equal to f of p, then this becomes 0. That means f of p must be p. Okay, so because this also has to be 0, then this is identically 0, so this has to be identically 0. So f of p is p. So this is again a new relation that you see. Okay, and after that, you'll write a general polynomial. It will be of this form. Okay, if the roots are from x1 to xn, so you can write it as this: a times x minus x1, x minus x2 till x minus xn. So what can f of p be like? What does that looks like? So they have p and f of p, they have same roots. Okay, so what can happen is that this constant can change, and then what you will have is that f of p will be k times p. Okay, so all the roots are same and only this changes. Or what can happen is that one of the roots is the same root is increased, so some xi root is repeated, so then you can write it as k times x minus xi of p, right? So you understand that, right? So there will be a xi term and that will get squared. Only that can happen because it can have only one power more. So f of p can look like this or it can look like this. Okay. And then when you again do f of p, then again you use the same logic. Either only since the roots have to remain the same, either only that constant factor is getting changed in this case, or here also either the constant factor changes or some roots is getting multiplied again. So it will become x minus xi and some x minus xj will be added to the factorial. Okay. So you can write it some x minus xi into x minus xj of the same thing again, p. And what you found is that this is equal to p, so the only possibility now is that if this is p, then it must be of this form. If it's this form, it has to be coming from this. So what does that mean? That means f of p must be some k times p. So what f does is that if it multiplies p with a constant terms. Okay, so that's the property of f. So we have already we're very close to finding what f is. Okay, we already know that it multiplies p with some constant number. So only the thing is now we have to find whether this constant is same for everything or whether it's like different for each polynomial or what. Okay, and so the way to do it is again you keep on playing with this relation with different kind of polynomials. So yeah, so this is what we found. We found f0 equals to 0, p f p f same roots, f of p is p, and finally we found that f of p is a constant times p. And now we are interested in finding the value of this k, because the k can also be polynomial dependent. Okay, so that's what you have to worry. So what I do is I look at these polynomials of the type x to the power m, a monomial which has only one term. So this, if you do f, it will multiply with k times of x to the power m. So you can add a suffix m because k can only depend on m. Okay. So again I have this relation, and this I will try to use this. Put p equal to x to the power m, q equal to x to the power n, and you just put it in that, and you get these two terms have same root. You just pull out one factor, so the other factor must be same, and what you get is that since these two are same, so kn is equal to 1 by km. Okay, that's what you get, and what you eventually end up is that kn times km has to be 1. Okay, so now what you do is you fix n and you vary m. So k1 k2 will be equal to k1 k3 equal to k1 k4 and so on, and all of them are equal to 1. So that means k2 k3 k4, they're all equal to 1 by k1. So next time what you do is you fix this one as 2 and you vary the other one. So put n equal to 2, vary m. Okay, so put k2 k3 equal to k2 k4 and so on, they are all equal to 1, and you put all of them as 1 by k. So this will be 1 by k1, 1 by k1, this will be 1 by k1, 1 by k1. So what you get is k1 square is equal to 1, and that means, yeah, so that means all ki square is 1, and that means ki is equal to either plus or minus 1. Okay, so this k can only be 1 or minus 1. It cannot be anything else. And now only thing you have to check is that does 1 and minus 1 works for the general case here. If you put k equal to 1, all the relations will be satisfied. F of 0 will go to 0, p and fp will have same roots, f of p will be p, this relation will also be satisfied. If you put k equal to minus 1, then also all these relations will be satisfied. So fp equal to plus minus p, it works, and it's also exhaustive. It cannot be anything else. So we already found what f is, and this is the way to approach functional equations. So I hope you you enjoyed the video, and if you are interested, you can write to me. So it was quite nice to see the mentioning of Vikram Betal. So this image is actually, you can recognize this is the image of that Vikram Betal from the Chanda Mama. It's a very old magazine, but still I think people know this image. So this one is made up of straight lines, and there are 20,021 straight lines. From there I made this, and you can see all these curves and contours which show up quite nicely. So I tried it with 2021, but then those lines were too less. So anyways, I hope you enjoyed the video, and if you have anything to say, you can email me, or you can also write in the comments below. And apart from that, thanks for watching, and I will see you next time. Okay, so bye.